Amsterdam, the Magere Brug. It looks as if it is easily movable. But how was this achieved? A movable bridge was originally used as a passive method of defense. It started with a timber span in a stone bridge. By setting fire to this timber structure, an obstacle was created for an enemy. Clever craftsmen, however, invented the prototype of the movable bridge, the drawbridge, which at the cost of much energy could be opened by means of a chain. The subsequent developments followed two different approaches. In the case of a drawbridge, reduction of the energy was achieved by using counterweights. Thus, equilibrium was obtained in the closed position. However, a serious problem was revealed. While opening, an acceleration occurred if a constant force was applied. This was obviously due to the increase in distance between the point of rotation and the chain. So, equilibrium was not achieved in each position. To keep this acceleration under control, the counterweight was sectioned. While moving the bridge, the action of the counterweight is transmitted in parts to the point of suspension on the wall. In a discontinuous way, this was achieved by using metal balls. By rolling a counterweight along a curved track, continuous control was obtained. In spite of these improvements, this development proved to be a dead end. More viable was the use of balance beams. This led to the bascule bridge with a counterweight in the balance frame. Until about 1800, these bridges were constructed of timber. Afterwards, this material was steadily replaced by wrought iron and later by steel. Now, equilibrium can be maintained in each position, thus requiring a minimum of energy to move the bridge. Integration of the balance frame in the deck gave birth to the bascule bridge. The ultimate situation is the same structure without counterweight. A combination of a fixed and a movable bridge is the transporter bridge, very popular around the year 1900, but now out of date. Passengers and motor cars are transported by means of a carriage or gondola. Remotely related to this type of bridge is the rolling bridge. This entire railway bridge is moved by means of rollers and cables. In this cantilever drawbridge, not only the width of the vessel is important, but also the mast. An old type of movable bridge is the derrick bridge, applied in fortifications and railway bridges. The main girders rotate with respect to vertical axes, placed in a saving in the abutment. This arrangement makes the opened bridge look like it's folded up. A floating bridge is an alternative to make a passage. Here, pontoons fulfill the function of the bridge and support the deck. A system of cables pulls the pontoons under the approach spans to let the ships go through. A next step in the direction of a swing bridge is this pontoon bridge. A rigid bridge construction, supported by a submerged pontoon at the nose of the bridge, leads to the pontoon swing bridge. At the lower flange, a bogie, including counterweight, is moved in the direction of the point of rotation. The nose of the bridge is lifted from the supports. The entirely submerged pontoon generates a constant upward pressure. Another application of a pontoon can be found in a swing bridge with a rim bearing. The pressure on the rollers, due to dead load, is reduced to about 30% by a pontoon in the pier. In this way, friction is reduced, and consequently the energy necessary to move the bridge. At the turn of this century, this system was used in some large swing bridges in England. To move the bridge, it has to be freed from the supports. A combination of drive and raising device is the tulp construction, an ingenious invention named after its designer. A pinion rotates a circular carriage by means of a toothed rack. The upper wheels pass along a coil-shaped track and lift the bridge and set it free from the supports. The bridge does not yet rotate, as one roller of the crank prevents this movement. The moment the bridge is lifted sufficiently, the crank rotates. The lower roller now follows the horizontal track. The other roller is supported by an inclined plane, which prevents the bridge from rolling back along the slope. In a symmetrical swing bridge, equilibrium is established naturally. However, this symmetry is a necessity in this aqueduct swing bridge. Symmetry because changing water level and the possibility of leaks must also be taken into account. To move this railway bridge, first a number of safety procedures are carried out. With a key system requiring a mandatory sequence, disconnection of the bridge from the signal system and rails is achieved. In these two unusual asymmetric swing bridges, two counterweights keep the bridge in equilibrium. One counterweight in the lateral direction, the other in the longitudinal direction. Equilibrium, a basic principle in movable bridges, is most clearly recognizable in a lift bridge. The lift bridge undergoes a vertical displacement. upwards with a limited air draft. Downwards with a limited waterway depth when the bridge is submerged. Most types of movable bridges did not adequately meet developing requirements and have ceased to be used. 4 types survived: the bascule bridge with overhead counterweight, the bascule bridge, the lift bridge, and the swing bridge. Movable bridges, constructed of steel and applied everywhere. A bascule bridge with overhead counterweight. The structure consists of the movable deck, the tie rods and the balance frame, including the counterweight. The balance frame is supported, in this case, by a portal frame. In this railway bridge, the bracing between the balance beams is missing. Here, the balance frame is composed of 2 I-beams, including a bracing designed as a Thierendale girder. This bracing is required to produce lateral stiffness against the wind and to prevent the lower flange from buckling. A part of the operating mechanism is housed in the columns. It moves the curved rack, thus opening and closing the bridge. In small bridges, the complete operating mechanism is housed in the columns. An electric motor drives the bridge via a gearbox, a system of shafts, and an open gear. In larger bridges, the drive is housed in a pit in which the motor, gearbox, and brake are placed. In order to guarantee equilibrium in every position, it is necessary to locate the pin connections in the balance frame and the deck at the vertices of a parallelogram. As a second condition, the virtual lines between the points B and E and C and F should be parallel. Here, E is the center of gravity of the whole balance frame. F is the center of gravity of the deck. In this case, the frame moves in between the columns. The point of rotation is situated immediately adjacent to the column. However, the point of rotation may also be situated above the column. This would limit the angle of opening of the bridge severely. For this reason, an offset column is used. In bridges with an orthotropic deck, separate balance beams are used. The bracing is missing. By separation of the balance beams, more counterweight can be installed. The beams are constructed like box girders. A box girder section possesses a large torsion constant and bending stiffness in 2 directions, making the structure less sensitive to vibrations. Equilibrating the deck takes place by means of the counterweight. It may consist of concrete, a mixture of scrap and concrete, or cast iron, usually put up in a box. Or, in the case of a broad bridge, a solid block of cast iron at the back of the beam. In bridges with a timber deck, the counterweight is placed in a box girder. In this way, a rigid connection is created between the beams, ensuring that the bridge rises evenly. A one-sided drive becomes possible. Correction of the counterweight may be necessary due to structural modifications made to the deck. Additional space for ballast blocks in the counterweight box is reserved and is accessible by hatches. The tie rods connect the balance beams with the deck. Thus, vibrations caused by traffic load are transmitted to the balance frame. This is taken into account in the design of highway bridges. These vibrations can be reduced considerably by connecting the tie rods to the front cross girder at the level of the neutral axis of the main girder. Alternatively, the tie rod is connected to a lift beam adjacent to the deck, which is connected to the front and back cross girder by means of a hinge-like construction. The deck of a modern bascule bridge with overhead counterweight is usually designed as an orthotropic deck. It is composed of a deck plate, stiffeners, and cross girders. A thin wearing surface is applied to the deck plate in order to reduce the dead load. This layer usually consists of a slurry covered with a layer of calcined bauxite, with a total thickness of about 8 millimeters. Operation of the bridge is possible by means of a crank connecting rod mechanism. A hydraulic system, or by means of a rack. A steel bar passing through or along the side of the column. It is provided with teeth or pins and meshed with a pinion. The mesh is maintained by a guide frame. The reaction at the front cross girder, due to dead load of the deck, is reduced to zero by the tie rods. To create a positive reaction on the supports, the rack contains a pre-stressed buffer. This buffer is compressed by making the pinion rotate a bit further, and the resulting compression is retained by the brake. Given a constant speed of rotation of the pinion, the movement of the deck is decelerated in the neighborhood of the support due to the curvature of the rack. In the same way, the compression of the pre-stressed buffer is achieved. As a consequence of the developments in electronics, the speed of the pinion is adjustable and a straight rack can do the job. By using a motor with electronic speed control, a prescribed velocity time diagram can be followed exactly. Brake loose, creep, accelerate, constant velocity. This type of bascule bridge can also be opened and closed hydraulically. The speed is controlled by a variable delivery pump or a flow control valve. A simple system may consist of a pump with or without variable delivery, a pressure relief valve to check the system pressure, a direction control valve, here in neutral position, a flow control valve to adjust the velocity of the bridge, a hydraulic cylinder, and a filter to remove abrasive and other types of contamination. These parts are connected by pipework. In this situation, the deck is assumed to be overweight and the wind is not taken into account. The direction control valve connects the pump and the cylinder. The piston rod moves and consequently the bridge starts to move. If the forces on the bridge become too large, the pressure in the pipework may become too high. The pressure relief valve starts working now to remove the excess pressure. In closing the bridge, the flow control valve is selected. Its operation is automatically controlled by the pressure distribution in the system. Because the action of the overweight of the bridge always works together with the action of the pump, the flow of oil tends to be greater. The flow control valve keeps the velocity of the piston under control, and so the velocity of the bridge. Bascule bridges with overhead counterweight are usually considered where the waterway width does not exceed 25 meters. However, in exceptional cases, a waterway width of 50 meters is possible. The deck may be constructed as a straight or a skew deck. If the bridge is built in an elevated situation, the counterweight may reach beneath the deck level. A parallelogram, a basic element of a bascule bridge with overhead counterweight, is recognizable in this complex steel structure. With a fixed counterweight, equilibrium can be maintained in every position. This special type, the Strauss type, was developed in America. Many examples are to be found in the harbor of Antwerp. The choice of a bascule bridge with overhead counterweight is mainly determined by the relatively low price because of the absence of a pit. Aesthetic considerations also play a part. If a wider clearance than about 25 meters is required, a bascule bridge is more advantageous. 60 meters or even more is possible for a single-leaf bascule bridge. Here, the total costs are severely affected by the presence of a pit. A bascule bridge is in fact a bascule bridge with overhead counterweight, in which the balance frame is integrated in the tail of the bridge. The four hinges are replaced by one center of rotation. And to fix the bridge in the service position, it may be equipped with a raising device. In bascule bridges, with or without overhead counterweight and a timber deck, an extra bracing is applied for reasons of rigidity. In the opened position and without bracing, the dead load of the deck would cause a deformation of the cross girders with respect to the weak axis. An additional function of the bracing is to carry the horizontal braking forces when the bridge is open to traffic. The section behind the point of rotation, the tail, moves in a pit or in free space. The bridge rotates with respect to a fixed point of rotation which coincides with the center of gravity. For dead load, the bridge should be in equilibrium in every position. Therefore, the center of gravity of the steel structure, the point of rotation, and the point of action of the counterweight must be located in one line. Also, in a Scherzer bascule bridge, the center of rotation coincides with the center of gravity. However, now the center of gravity is moved horizontally. The teeth on the quadrant track are necessary to fix the point of contact of the track and the quadrant. A more advanced solution is the center stub. Good contact between the stubs and quadrant is achieved by giving the stubs an involute profile. A bascule bridge with a fixed axis usually has a closed pit. The tail of the bridge is hidden from view by the road construction, which also forms the ceiling of the pit. In an open pit, the traffic runs across the tail of the bridge. A disadvantage of this solution is that while opening, all dust and dirt on the deck falls into the pit. This is why this type of bridge is not preferred. In the movable condition, the bascule bridge is supported by two trunnions, each with a spherical roller bearing or a spherical plane bearing, made in an extremely precise production process. Turning, grinding, hardening, and tempering. And then a fine machine finish. In spherical roller bearings, the rollers in the outer ring have common spherical track. The two tracks of the inner ring are each positioned at an angle with respect to the axis of the bearing. Between the two rings, the spherical rollers are placed in a casing which has a high resistance to abrasion. The bearings are self-aligning and are therefore insensitive to deflection of the trunnion. Mounting the various components together is carried out with utmost care. The smallest plastic deformation will have an adverse effect on the lifetime. By applying roughness tolerances within very close ranges, a minimum internal friction can be achieved. Finally, the radial clearance is checked to ensure that it is within the acceptable tolerance range. A new development is the spherical plane bearing, in which discs of polyamide reinforced with glass fiber are used. Size for size, these spherical plane bearings can carry greater loadings, leading to smaller dimensions. They are resistant to vibrations and micro displacements, such as may be met in bridges. To ensure enough room for the main girder of the bascule bridge to rotate over an angle of about 80 degrees, the bearings are placed on brackets in the pit. While rotating, the stress distribution in the bridge changes continuously. The double symmetric point of rotation of this bridge will be used as an example. The stress distribution is calculated for dead load, for rotation from the closed, movable position up to the opened position. The colors indicate the equivalent stresses within a certain interval. Violet, a high stress in the interval between 105 and 120. Light blue, a low stress between 0 and 15 newtons per square millimeter. In the closed, movable position, the stress distribution is symmetrical with high stresses in the upper and lower flange and low stresses in the neighborhood of the trunnion bore. The stiffeners reduce the stress locally. During rotation, the bending moment and shear force diminish and the axial force develops. At an angle of opening of about 50 degrees, this effect can be observed clearly, as symmetry in the stress distribution is lost. In the vertical position, bending moments and shear forces are missing. Again, a symmetrical stress distribution occurs, but now with a low overall stress level. A detail from the calculation. The stress distribution in the trunnion bore in the closed, movable position. The color bar is adapted to the new situation. Again, the symmetry is to be noted. The area of contact of the trunnion bore and trunnion can be easily spotted. Due to hole deduction at the point of rotation, the web of the main girder is locally made thicker. To resist wind loading in the opened position and to guarantee stability, stiffeners are necessary. Stiffeners 50 millimeters thick are welded to the web, which is 70 millimeters thick. Research at T&O has shown that using steel with low carbon equivalent, especially a low carbon percentage, combined with the use of vacuum-packed consumables with very low moisture content, makes preheating unnecessary. This means an improvement in quality and an increase in productivity. A local change in direction in the upper flange near the transition from tail to deck causes a concentrated load perpendicular to the flange. This transition should take place smoothly. A stability problem arises in the compressed lower flange near the point of rotation, in particular in service conditions. This can be taken care of by supporting the lower flange laterally. Counterweight material, usually concrete, is used, often housed in a steel box. By using a hinged counterweight, the lever and the point of action of the counterweight are fixed exactly. In this case, a deeper pit is required. In all types of bascule bridges, a rack can be used to operate the bridge. Also in this case, a guide frame keeps the pinion and rack in mesh. The same movement is achieved if we make the pinion move along a curved pin rack. In the operating machines of this bridge, a toothed rack is used. The end of the rack may consist of a shell construction, which produces a smooth deceleration during lowering of the bridge, and next raising. While the electrically driven pinion maintains a constant speed, the curvature changes at the place where the pinion leaves the rack and moves on to the shell. The shell rotates and the curvature increases. This reduces the speed of the bridge. Over the last part of the shell, the curvature is constant and consequently the speed is reduced to 0. This part of the shell is used to raise the tail of the bridge, achieving a positive reaction at the nose of the bridge. The Panama wheel was originally developed by Gustav Eiffel to operate the lock doors of the Panama Canal. It consists of a circular sector with a pull-push rod connected with hinges to the sector and the bridge. During closing of the bridge, deceleration takes place automatically because the speed of the hinge in the direction of the pull-push rod reduces to 0. In this pull-push rod, a pre-stressed buffer is used, making it possible to create a positive reaction in the closed position of the bridge. This system has one disadvantage. Due to a temperature gradient, a curvature in the deck may arise. This means that the support of the bridge is reached at too high a speed because deceleration takes place over too short a distance. With an electronically operated drive, this disadvantage can be avoided. The ideal velocity to approach the support is about 3 centimeters per second. An alternative for a Panama wheel is the roller slot system. A rotating crank at the end, provided with a roller, acts in a slot and moves the bridge. The same system is also possible with a hydraulic drive. Similarly, as in a Panama wheel construction, it may happen that the bridge touches the support with too high a speed due to a temperature gradient. The next step in the development is a direct operation of a bridge by means of a hydraulic system. The high forces which can then be achieved make it possible to deviate from strict equilibrium as a design option. Obviously, an overweight of the deck causes a positive reaction at the nose support. If no overweight is present, the bridge must be lifted at the other end. The movable bridge is transformed into a fixed bridge by means of a raising device, making the bridge less sensitive with respect to vibrations. In this bridge, The counterweight is housed in a construction supported on the axis of rotation and the tail of the bridge. At the end of the closing maneuver, a hinged column is moved under the counterweight, which is then carried by the column and the axis of rotation. The movable bridge now behaves like a fixed bridge. This principle is in common use, especially in railway bridges. An ingenious but complicated solution is the yoasting system. The bridge is raised by means of a lever, a balance frame inside the bridge. Then a support beam can be removed. Now the bridge is in a movable position. An interesting alternative is the tail bridge, a combination of the two types of bascule bridges. The columns make a pit redundant. However, because the deck reaches so high in the air, the wind loading increases. Bridges are loaded by fluctuating wind loading during opening, as is shown in the upper graph. Assuming a speed-controlled motor, which produces loading as shown in the center, which results in loading on the drive, which is superimposed on the dynamic loading due to moving the bridge. The lower graph shows the result of such a simulation. With rigidity, buffers, masses, and dampers as parameters, and a random wind loading, the instantaneous motor torque is calculated. In very windy areas, reduction of wind loading can be achieved by constructing the deck as a grid. Wind loading is a factor not to be underestimated. Also in other types of movable bridges. Single-leaf bascule bridges are possible as well as double-leaf bridges. In this way, a greater waterway width can be obtained. An unrestricted air draft can be achieved with a bascule bridge. In a lift bridge, a greater waterway width is possible, but the air draft is limited. The main parts of a lift bridge are the towers, made of concrete or steel, and the deck in between the towers. Counterweights are placed in the towers or outside the towers. The deck is connected to the counterweights by means of counterweight cables. Starting with a design option in which equilibrium between deck and counterweights is obtained at half height, this equilibrium is disturbed when the bridge is moved. The cable length to the left or to the right of the sheave is shortened or lengthened. Shifting the action of the cable weight to the right or to the left. A disturbance in equilibrium induces acceleration. To counteract this effect, a balance chain is installed. Outside the tower or inside the tower. Dead load equilibrium is now maintained in every position of the deck. However, a positive reaction of the support in closed position is no longer guaranteed. The wind is the disturbing factor, which can be accounted for by friction between the counterweight cables and the sheaves. The positive reaction is generated by exerting an extra torque on the sheaves by an elastic coupling, fixed by the brake. This reduces the stress in the cables between sheaves and deck. Another design option might be add some extra weight to the deck to guarantee the downward motion of the bridge and a positive reaction. The bridge is moved by a separate system of cables, which pulls the counterweight downwards. If approach spans are present, the towers may be placed on these spans or be founded separately. Where the towers are supported by these approach spans, the temperature gradient should be accounted for, as deformations due to this temperature gradient will arise. The tower tops move toward one another and the deck may stick. To prevent this, care should be taken to provide for sufficient clearance between deck and towers. The deck is fitted with guide rollers, rolling up and down the faces of the towers. The counterweights can be made of steel. Concrete is a factor of 3 lighter than steel and needs a greater volume to obtain the same counterweight. The cables are connected directly to the counterweight, or by an equalizer distributing the same load to each cable. Cables are distinguished by their method of manufacture. Lang's lay cables, called after the Englishman Lang, and normal lay cables. In Lang's lay cables, the wires in the strands and the strands themselves are wound in the same direction, both to the left or both to the right. However, in normal lay cables, the wires and the strands are wound in opposite directions. For instance, wires to the left and strands to the right. The flexibility of a Lang's lay cable is greater than that of a normal lay cable. This is why Lang's lay cables are used in lift bridges. The cable end connection consists of a socket filled with a special resin. The strength is more than sufficient. Tensile tests show the rupture always to occur outside the socket. After fabrication, the cables are stressed for 36 hours up to 1/3 of the ultimate load. This is how the major part of the structural strain is removed. When the stress is removed, the cable will slightly unwind. In order to mount the cable with the correct length, one side is painted to show one line. If, after mounting, this painted line runs parallel to the cable axis, the cable has the same length as measured while stressed. If the bridge is open to traffic, the deck must be fixed vertically and brought in the correct position in the longitudinal and lateral directions. By means of overweight of the deck or a locking pin, the vertical position can be fixed. A pin necessary for centering in longitudinal and lateral direction also adjusts the rails. Buffers reduce the kinetic energy just before the bridge touches the supports. The locking pin fixes the bridge vertically. Without precautions, the deck of a lift bridge might adopt a slanted position while moving. Synchronization, leading to a horizontal movement up as well as down, can be achieved by using a special cable system. In this situation, it is impossible for the bridge to rotate clockwise. A second cable prevents the deck from rotating anti-clockwise. So the deck has to move horizontally. Another system, the mechanical axis, requires a connection between the towers. A steel shaft between the towers enforces synchronization, as the differences in level are limited by torsion in the shaft. An electrical connection can be produced by using induction motors. A rotor is moved by a rotating magnetic field, inducing an alternating potential in the rotor windings. Difference in phase means difference in potential. Connecting the corresponding rotor windings removes this difference in potential and so difference in phase. The motors are forced to keep in phase and synchronization is guaranteed. Synchronization is easily achieved in direct current motors. A tachometer measures the speed of rotation of the motor. In this model, a difference in angle is introduced, shown by the difference in time at which the arrows pass point 0. Difference in angle leads to difference in potential and then to correction. Distance between the motors is of no importance. A roll-on, roll-off bridge can also be considered as a lift bridge, though adaptation of the bridge and the operating mechanism is necessary. The bridge is supported by a vessel leading to a specific problem, tilt. This is the change in rotation of the ship during embarkation. It would cause torsion in the bridge. Moreover, the trim of the ship changes as well as the level, as the ship is subject to tidal movements. The change in rotation is accounted for by making hinged connections between main girders and cross girders. The ramp plates between bridge and ship give adaptation to the shape of the ship and also partially to the tilt. Tilt, trim, and tidal movements should be accounted for in the operating mechanism. Again, the bridge is kept in equilibrium by counterweight cables between bridge and counterweight. In the operating cables, a loop is introduced, including a relatively small counterweight, the cable tensioner. In this way, clearance is created. The bridge can follow the displacements of the ship without effect on the motors, because the cable tensioner and the clearance produce a constant tension in the cable. When the cable tensioner is lifted and the clearance between support and tensioner is exhausted, the operating cables become effective to move the bridge. During the movement, the cables between the deck and the counterweight remain vertical because the lift girder is guided vertically at the towers. That is why, at the abutment, a toothed roller support is installed which allows horizontal displacements due to the vertical guidance and the temperature expansion. For a lift bridge, the width of the deck is of no importance. A lift bridge with only 2 towers was the optimal solution in this situation, with limited air draft and a wide central verge with 2 wide carriageways. In a swing bridge, the width of the bridge should always be smaller than the length in order to achieve sufficient clearance. There is no limit to the air draft. The bridge width determines the diameter of the pier, but pier or bridge width reduce the waterway width. A swing bridge consists of a steel structure with 2 equal or unequal leaves, supported on 1 point of rotation. A drive, and the end supports, including a raising device. Counterweight is only necessary in asymmetrical bridges. A swing bridge is protected by fenders, as the bridge in opened position and the pier are vulnerable to collisions. A plate girder as main girder can be chosen, or a simple cable-stayed girder. A modern cable-stayed swing bridge and a truss The swing bridge is supported either by a rim bearing or on 1 point of rotation. The point of rotation coincides with the center of gravity. As in this situation, the bridge is exposed to wind effects. 3 or more balance wheels are used, which limit the tilt of the bridge in the movable position. A rim bearing changes the swing bridge in service condition into a girder on 4 supports, of which the central span is relatively small. Loading on one leaf introduces an upward deflection of the other leaf, and the reaction on one support on the pier may reduce to 0. To prevent this, the central part is equipped with a light truss system, which allows shear deformation to occur. In this way, the bridge rests on all supports, even if unequal loading is applied. Still better, however no longer in use, this force distribution can be obtained by a pull rod with slot as a connection between bridge parts and tower. As the roller track of the inner circle is shorter than the track of the outer circle, the rollers are tapered. Due to sensitivity with respect to tolerances, deformations and subsidence may happen, but not all rollers are load carrying. This disadvantage is removed in modern constructions by replacing the rim bearing by a spherical roller thrust bearing. It consists of an inner and an outer ring in which a carefully machined cage is fitted. In that cage, the spherical rollers can rotate. This bearing type is self-aligning, which makes it insensitive to angular misalignment of the axis to the housing. The spherical roller bearing is a part of the total rotation point construction and can only transmit radial and axial forces. Another type is the slewing ring bearing. The inner and outer ring are provided with a pattern of holes so that they can be connected directly to the bridge and the foundation. On one of the rings, teeth are provided, by which the rotational movement can be obtained. If a small rotation with respect to the horizontal axis is allowed, and with the center of gravity just outside the point of rotation, a raising device can be applied on one side. As the supports are removed, the bridge will slant and the centering comes free. The other side will come free from the supports at the same time. In another type of raising device, the bridge is fixed with wedges. In this type of raising device, eccentric rollers are used. The eccentricity takes care of the clearance and compensates for the deformation due to dead load and temperature gradient. To reduce the effect of the temperature gradient, the upper beams of this bridge are painted white. Also, a swing bridge can be raised by a hydraulic jack in the center of the bridge. By using eccentric connection of the pull-push rod, the Panama wheel can rotate over 180 degrees and acceleration and deceleration take place automatically. The wheel is the intermediary through which the pinion transmits the movement to the bridge. The pinion has a constant speed and is moved electrically. In big swing bridges, the transmission is achieved by direct action of the pinion to the toothed rack. The pinion, mounted in a frame fixed to the bridge, reacts against the pier, which in its turn is connected to the ground. In another solution, the drive and the pinion are combined in a so-called locomotive. It drives along a toothed rack on the pier and moves the bridge by means of a pull-push rod. Another example is an open gearbox. A crank and a pull-push rod are driven. In fact, this is an alternative for the Panama wheel. In a hydraulic system, the pull-push rod is replaced by the piston rod of the cylinder. Based on the principle of pinion and toothed rack, old bridges are simply moved by hand. The bridge master moves the bridge and at the same time controls the acceleration and deceleration. Speed control, an important aspect for all bridge types. In some old bridges moved by a motor, the speed control is still carried out by hand by the bridge master. But in modern bridges, the speed control takes place electronically. Or the control is operated by the bridge itself by means of proximity sensors. These sensors are activated and the motor reacts. Remote operation is possible thanks to the developments in electronics. Simply, with direct visual control, or from one bridge master cabin, two bridges can be attended to.
Attentie, attentie. De brug verlaten. De brug staat open.
Alternatively, here is a central remote operation where 3 bridge masters attend to 15 bridges.